Hey, this is Leach with Simpson Math, and in this video, we'll be talking about solving systems of linear equations in two variables. So let's get started. So to be clear, when we're talking about two variables, we're talking about x and y. So then we're talking about an equation that can be graphed on the xy plane. And in this video, we're going to be just talking about linear equations. So let's look at the three possibilities of if I have lines, how they can intersect and interact with each other on that xy plane. So the first option is that I can have one solution, and that occurs when we have this one intersection. So if I have this blue line intersecting with this red line, it intersects at this point. Now remember, we reference points on an xy grid as an ordered pair, x comma y. And in this case, that it's an x value of 1 and a y value of -2. And we put parentheses around that to denote that that's an ordered pair. So what that means is if I plug in an x of 1 and a y of -2 into this blue equation, we'll get some value out, some number. And if I plug an x of 1 and a y of -2 into this red equation, I'll get that same value out, that same number, meaning that they will equal each other. And in this particular system of equations, system of this blue and this red line, they are only going to have one point, one ordered pair, one combination of x and y's that would produce the same number if I plug both x and y in. And it's, in this case, at that 1, 2. We just have that one intersection. Nowhere else is this line is not going to curve and like swoop back around and intersect the red line, only that one time. So then we could have parallel lines. So if I have parallel lines, because if parallel lines, if you recall, they never touch, they never intersect, they're going to stay that same distance apart. They also have the same slope. So they're never going to touch. There's never going to be an xy pair that I could plug into both the blue and the red lines that I would get the same value out. So we're going to have no solution. And what I mean by false statement here is often when you're working these systems of equations, you might end up with getting something like that says 12 equals 5. Well, does 12 equal 5? No, that's nonsense. So often if you see something like that, we've produced a false statement, and when working with systems, often the case is that we're looking at parallel lines. And the third case when we are dealing with lines is that we might just have the same line. So I have two separate equations, and when you first look at them, they don't look like they're the same line. But they're actually the same line. They're actually on top of each other. So what we say is that we have infinite solutions. Well, that's because I could pick this point. I could pick this point. I could pick this one, this one. Ones that go way up there, ones that go way down here. Any point on the line will function as a solution to this system. Now, it's not any point, because if I pick this point, that's not a solution. I'm not going to get a true statement from both of those. So only any points on the line, but there's an infinite number of them. That's why we say infinite solutions. And again, what that true statement means is you might be working the system and you end up with a true statement, 12 equals 12. And then that goes to show that we're likely going to have infinite solutions. And you'll see an example of both these no solution and infinite solutions in this notes. One way to solve systems of linear equations is to solve them by graphing. Now, I'm including this equation for a few reasons, but really at the end of the day, it's not terribly important to me. I'm not really going to be doing there's not going to be too many times when I'm going to ask y'all to solve a system by graphing. But I'm including it, one, just to review graphing lines, two, to hammer home what's happening with these systems of equations is that we do get that our solutions can be done graphically, and that's when the two lines intersect each other. And also, this is providing me an opportunity to review some simple solving techniques. So let's get started with that. So I have this system of equations. It is 4x plus y equals -4 is our red equation, and then our blue equation is 5x plus 2y equals -2. So I have a tip right here. It says that I'm going to solve my two equations to put them into slope-intercept form. So I'm going to solve them for y. When I do, I'll get that m, which we denote as the slope, and I get b, the constant, which we denote as the y-intercept. I know it's the m because it is multiplying by the x. It's the x's coefficient, and that b is a constant is by itself. It does not have the x on it. So let's review solving and solve this red equation for y. So for this red equation, I need to get this y all by itself. Well, good news, when I look at that y, I see the coefficient of y. Well, actually, I don't see the coefficient of y because it's an implied positive 1. So that's good news. So I don't have to worry about the coefficient there, but I do have this 4x in the way. So I need to move this 4x. So whenever we're solving equations, recall that you can basically do whatever you want as long as you do it to both sides and it's mathematically legal. So I can subtract a 4x from both sides. So here I've subtracted 4x from the left side and I've subtracted 4x from the right side. Well, 4x minus 4x, that cancels to 0. And so we really have in the next line 0 plus y equals what's on the right-hand side. And then over here on the right-hand side, a -4 and a -4x, those don't have anything in common. They are not like terms. I can't add or subtract them together. So I'm just going to write them each separately. So we end up with -4x minus 4. Right? So let's go to the graph and let's graph that. I already have it done for us over here on the right, but let's go through it. So we always start with our y-intercept because that pins the graph down. So I have a y-intercept at -4. So over here on my graph at -4, I would place my first dot. And then I have a slope of -4. Well, if I have a slope of -4, I like to think of, I'm going to just draw a quick little picture right here. So imagine that this is literally Mario, and those are the hills that always have eyes for some reason. And so we have Mario right here, and he's going to be running up the hill, down the hill, he can be flat, or he's going to jump, and there's nothing on the other side, and he's going to jump to his death. But if you have that picture, notice that Mario is running over here, he's casually, we would say, up the hill, and Mario runs in traditional side-scroller 2D games as from left to right. Notice there he's running up the hill, so positive, right? Over here he's running down the hill, so we'd say that that would be a negative slope. This type of line, when it's just flat, it's going to be a slope of 0. And then, oops, lost my picture. Maybe clarify that. So positive, negative, 0, and then this is no slope. All right, so I remember being in, I should have probably learned it in Algebra 1, but it was actually, I think, my Algebra 2 teacher. She was really quick on these little mnemonics, and this helped me keep straight the positive, negative slope and the difference between 0 and no slope. So horizontal lines are slopes of 0, and this is, if it's a vertical line, it's a slope of actually no slope. And I can think of this slope of 0 because it is what is between positive and negative. All right, so we have our positive slope, then we have our negative slope, and that is what's in between it. And 0 is between positive and negative numbers. So I'm going to graph my line over here of a -4, 1. So our slope is -4, but it's -4 over 1. And if you recall that the slope is the change in y over the change in x. So that's that -4 over 1. So that means I'm going to go up and down 4, left and right 1, but do that in a way that it's going to produce that negative slope. So I'm going to come over here. I can go from here, I can go up 4, 1, 2, 3, 4, over 1. But don't stress so much about the directions, and some people get caught up in the up or down or left or right. Just move in a direction that's going to make it be negative. All right, so if I move it over here, then it would produce a line here that would be going a downhill. It'd be sliding down a hill that way. So we have our next dot there that can continue that pattern. Up 4, left 1, and there we have our line. All right, a little bit faster now, so let's take a look at this one. So for 5x plus 2y equals -2, ultimately I need this y to be by itself. So that means both the 5x and the 2 need to be moved. If you recall from my order of operations discussion, we talked about gamma, so grouping, exponents, multiplication, division, addition, subtraction. And so whenever you're trying to simplify, we follow down that order of operations. But when you're solving, we go backwards up the order of operations. So looking at that, I have this y that I need to get by itself. The freest thing, the easiest thing to take, imagine you have a box packed full of stuff and you need to get something at the very bottom of that box. The easiest thing to get out of the box is something that's on top. But something that's crammed over and around and directly on top and stuck on top of the thing that we need to get, well, that needs to come out later. I need to get the easy things off first. And so the easy thing to get off first is the addition and subtraction items. So let's take that 5x, subtract a 5x from both sides. Again, these two things are not like terms, so we just write them separately. And this cancels to 0. All right, so now we need to divide by 2. When we divide by 2, 2 divided by 2 will reduce to 1. You might be familiar with someone just drawing a big divide by 2 on the right-hand side, but I like to put a divide by 2 over each thing if I know that I'm likely going to reduce them. And I see over here, I see this -2. So I'm going to go ahead and say just you get a divide by 2 and you get a divide by 2. They both get a divide by 2. This one already had 1. So that way these 2's reduce to 1. And -2 over 2 will reduce to -1. So it's okay to kind of separate that division and get them both separately. The math behind that, in case you're like, is that legal? So if I had, let's just say -5 halves plus that 2 halves, I would be able to add that together, and it'd be that -5 plus 2 over 2, right? So if I can go this way and with common denominators and add them together, I could also basically unadd the fractions. So that's also like a way to think about it. If you were to say big divide by 2, you could break the fraction apart and end up with what's here as well. So that's also another way of thinking about it. So again, look at the verbiage. These canceling of items, I'm subtracting and getting 0. So we casually will say cancels to 0. Please don't say reduce here, say cancel. Over here though, these 2's, they are reducing to 1. Now over here, this one is reducing to -1, but the 2's themselves are reducing to 1. They are not canceling, they are reducing. So it's a little bit of just a verbiage that whenever we talk, if you make videos for me, to make sure that you're using that language correctly. All right, so then let's graph this blue graph. So it's, we have our y-intercept at -1, and then we have our slope of a -5 halves. So I'm going to start with this -1 and put a dot right there. I have a slope of -5 halves. So again, it's a negative slope, so I know that it's going to be going downhill like that. But it's going to have a change of 5 up and down, and change of 2 horizontally. So from this point, I can go up 5, 1, 2, 3, 4, 5, and I'm going to choose to go to this left because that will produce it being a negative slope, which is going to be going downhill like that. So up 5 over 2, and then I can do that in the same direction, do it on the other side, so I can go down 5, oops, that's my eraser, down 5, 1, 2, 3, 4, 5, over 2, 1, 2. This way, it's going to, again, produce that negative slope. So when I do this, I notice that they both, they intersect here at -2, 4. So the solution to the system is -2, 4. Let's check this. So if someone said, hey, I think a solution to this system is -2, 4, let's check it out. And you didn't want to have to graph it. Well, what you could do, because it's a solution of both, it should be a solution to both of them, I should be able to plug in -2, 4, and I should get a true statement out of both. Now, this getting a true statement is not the infinite one that we saw before, because I'm just plugging this into each one independently. So if I take this -2, 4 and plug it into the red equation, so plug in a -2 for x and a +4 for y, I end up with -8 plus 4 equals -4, which I do end up with -4 equals -4, which is a true statement. So I know just from that moment, so if erase all this from your memory for just a second, pretend that we hadn't done that already. So what this tells me is that negative 2, 4 is somewhere on that red line. All right, I don't know about the blue, but I know that yes, if I plug in negative 2, 4, it is on that line. Like, for example, if I plugged in 3, 1 right here, I'm not going to get a true statement. All right, so that would be an example of getting a false statement. And I know, well, 3, 1's not on that red line, but I just found out that 2, 4 is on the red line. And just to note, I'm using this little equal question mark. This is a valid mathematical symbol when you're doing tests, because you're saying, well, I don't know, I'm determining, do they equal each other? I haven't made that determination yet. And then I've dropped the question mark when I'm like, yes, negative 4 does equal negative 4. So over here, so take negative 2, 4 and plug it into the blue equation. Plug it in and I get, plug the negative 2, 4x in and I get negative 10. Plug the 4 in for 4 in for y and I get 8. And then I can add those and get negative 2 does equal negative 2. So again, that is showing that they are, that negative 2, 4 is a solution to this system. So like I said, this was a bit of a review example, reviewing graphing lines, reviewing solving for y, reviewing how to just check and see if a specific point is a solution to even just one line, and then we see that they work in both, so it is a solution to the system. Our main focus, though, is going to be over solving our systems of equations algebraically, and we have two methods, substitution and then the addition or elimination method, two different names for the same process. Let's first take a look at the substitution method. All right, there are 4 general steps when we are solving by substitution. The first one is to solve either equation for one variable, so solve for x or solve for y. So we just did that when we were graphing. We solved for y for both. But for this one, you just need to pick one of them and then solve for x or y. Here's a little hint. Look for coefficients of 1 or negative 1. Those are going to be the easiest to solve for. And if you have one that is a coefficient of 1 or negative 1, what makes it easiest is that you're likely to not end up with fractions because you're not going to be having to divide that coefficient out. And then once you get that, you're going to substitute the expression into the other equation, and then we'll solve, and then we're going to do something we call back substitute. So we'll back substitute the value you get into either original equation and then solve. So step 1, solve either equation for one variable. So looking at this system of equations, this is a different system than the one we had a second ago. One of these variables is just screaming at me saying, I'm the easiest one to solve for. Do you see this x? This one is going to be the easiest one to get by itself. If I was to solve for this y, I would have to, 1, move this 5x, but then the big kicker is dividing by negative 4. I don't want to divide 9 or 5x by negative 4. That's just going to produce fractions. Same thing if I try to solve for this x, I would be having to divide everything by 5, and those don't divide by 5 evenly. Same thing with this y. If I was to divide everything by negative 2, which I know you don't do it in this order, but notice those fractions. Gross, right? But if I was to solve for the x, which all it does just requiring is me just adding a 2y to both sides, then I don't have to worry about any fractions. So that's exactly what I've done here. I've taken the second equation, this red equation, and I'm solving it for x. So I'm adding 2y to both sides. They cancel to 0. And so I know that there is this relationship between x and y on this red equation, but here's this solved for x. So that's step 1 done. All right, step 2, it says to substitute the expression into the other equation. This is important that you put into the other one. I'm using colors here to help me keep track of that, so that might be a thing that might be helpful for you. So here I have this red equation, and I'm putting it into the blue equation. If you were to take this red equation and put it into itself, here you will end up with a true statement, but that's not going to be proving that anything is the same line. That's going to be an error because you're just putting the equation back in itself, so of course you're going to get a true statement. So make sure it goes into the other equation. So here this is just substitution. So I'm taking this 2y minus 3 and putting it into that x. And so we did this last lecture with function notation. So it's not written in a function, but it's that same idea. I'm replacing x with 2y minus 3. And then now we just need to solve for y. So I distribute the 5. And so we have 10y minus 15. And then it's always a good idea to combine like terms before you start moving things around. So I'm looking here, I see this 10y and this negative 4y. Those are like terms, so let's pull them together. And so I actually really only have 6y on this left-hand side. So now that I've done that, now that I can start solving for y. This 6 needs to go and this negative 15 needs to go. But again, which of those is easiest? Well, the addition and subtraction is easiest to move first. So I'm going to add 15. Notice we're adding because this is a negative already. So negative 15 plus 15, that cancels to 0. These are like terms. Those are just numbers, so I can add them together and get 24. And then here I can divide both sides by 6. 6 divided by 6, that reduces to 1. 24 divided by 6, and you're left with then 4. So you have y equals 4. I do have this note over here that often you see, in this lecture you're going to see me have this, the little algebra notations about plus 15 divided by 6 divided by 6. And I often do them in green. I just find it easier that way. But here's just something, a little picky thing about me. For me, I don't have to do this. If I'm working a problem by myself, I don't need that plus 15. If I'm working a problem by myself, I don't need that divide by 6. And I'm okay if you know what you're doing. You don't have to write those steps either. You should communicate them somehow. Like especially if you're making a video, you can say add 15 to both sides without having to write that. But it's kind of an understood thing at this step, at this point with college algebra. This is quite a prerequisite skill. So I'm not requiring to see that. But here's this note. If you include them, you have to do it fully. I have many students who they will write right here plus 15, but they will not write it on this right-hand side. And to me, that's a problem. If you're going to do the notation, you need to do it fully. Because if I was to just add 15 to this left-hand side, this right-hand side would remain at 9. It would not become 24 all of a sudden. Okay? So either don't show me notations at all, or show me all the notations on that particular step. All right? So oftentimes I might not show this step, but the divide by 6 is kind of easy enough that I might often show that, but without doing that. So you don't have to commit to all notations ever, but for a given step, you need to show me that you're adding 15 to both sides, or here that you're dividing by 6 on both sides, right? Not just one side, because that would be a problem. Okay, so just to be clear, I kind of rambled there for a second. So we solved for x on the red equation, plugged it into the blue one, and now we have y in the now we've determined for sure that my y equals 4. So in terms of graphing, somewhere we know that these two lines are probably going to cross, and if it does, or not probably, that it does cross, and then it does cross at a y of 4. So when I go up to 4, somewhere it's crossing when y is 4. Now we need to nail down where that x is. So I can do that by plugging this, and I can put this y equals 4. I can put this back into either equation. So this says either original equation, and you can put it to that. So I'm going to just put it back into the red one. So I'm going to plug in a 4, and I end up with negative 8. So x minus 8 equals negative 3. Add the 8 to both sides, and then I end up that x is 5. So I have an ordered pair of 5, 4. Now, this is a little bit of a technical note, but I would like you to put your ordered pair in a set, because this is a set of ordered pairs, but it just contains one thing. The reason why this matters, it's just a little bit of just being a little bit more formal, but I could ask you, we're not going to, but I could ask you to graph a parabola and a line, and then in this case we would have two solutions, so it would be that set, so we would have a second ordered pair inside of that set bracket. Later, when we have infinite solutions, that's a set of many. And technically, when we have no solution, it's the empty set. So this is just a technical mathematical thing. I would like you to put the set notation brackets around your set of ordered pairs. All right, so then just to verify this solution graphically, this is not a required thing, but just so that way you're clear, that red line, if I graph the red line and graph the blue line, they do intersect at 5, 4. This here shows you that you don't have to plug the y equals 4 into the original equation. You are able to plug this into the solved equation. We've already previously have solved the red equation for x. I could just plug the 4 directly into that and then just simplify. And that's actually really a lot easier because look at this plus 8. We did that up here when we solved for y, but we just did that in the form of a plus 2y. So it's kind of a little bit redundant. You've already done that. So you can also just plug it into one that you've already solved for one of the variables. That will save you a little bit of time. All right, our next example, you're going to do on your own. I want you to see how you can handle it. But just a little hint is that make sure that you solve each system for ax plus by equals c. Now, there's a few reasons to this. One, it lines up a little bit more with what we're doing when we move on into elimination and addition. But also, just look at this. You want to figure out which variables are easiest to solve for, and this x and this y aren't necessarily going to be the easiest ones to solve for because you're going to have to combine them with these others, x's and y. So get all of our variables together, get one instance of each variable in each equation for you to decide which variable is going to be easiest to solve for, and then proceed with the substitution. So go ahead and pause this video and try this one on your own. All right, welcome back. Let's see how you did. All right, so again, like I said, we need to solve them or put them kind of in the same form, or get really, at the end of the day, I just need to get one instance of each variable per equation. So here I've chosen to subtract the x from both sides and also added a y to both sides. Those x's and y's have canceled to 0. 3x minus x is 2x. Negative 4y plus y is a negative 3y. So my blue equation is 2x minus 3y equal 4. Then over here, I had these two y's that I needed to get together. So I'm going to subtract the 5y from both sides. 5y's cancel on the right-hand side, and I'm left with then just 2x plus y equals negative 4, and I rewrote it over here. All right, now that I have my set of equations that are simplified, I just have one instance of each variable, I can now determine that this y is going to be the easiest one to solve for, mainly because it has a coefficient of 1. All right, if you were to solve for any of these other variables, you would end up with fractions. It does not make it impossible, but I know that you probably don't like fractions that much, and that just makes the math that much harder. So let's solve for this y. So I'm going to rewrite the equation just for clarity. 2x plus y equals negative 4. Subtract the 2x from both sides. What happens when I do that? The 2x minus 2x, they cancel to 0. So it's now a 0 plus y. And then negative 4 minus 2x, they go together. They don't go together. They are not like terms. So I have negative 2x minus 4. Then we take this y value. So y equals this. This is a true fact about y in the system. Y equals this relationship between x. So I can take this and replace the y in the other equations. It's really important that you put this into the other equation, and I'm color coding to help me do that. So I'm going to replace this y with negative 2x minus 4. Again, with the parentheses, you have to put parentheses here because this negative 3 is multiplying both the negative 2x and the negative 4. So we have to have these parentheses. So we distribute. 2x is still there, and then we have negative 3 times a negative 2x is 6x, and a negative 3 times a negative 4 is a positive 12, because negative times negatives are positive. All right, combine like terms before we start simplifying. Before we start solving. So 2x plus 6x is 8x. All right, so now I have on each side, I have my variable, and then my constant, everything simplified. So I can subtract 12 from both sides. That cancels to 0. 4 minus 12 rather is negative 8. 8x equals negative 8, so I can divide both sides by 8. Negative 8 over 8 reduces to negative 1. All right, so on my coordinate grid, I know that somewhere when x is negative 1, which is that dotted line I just drew, somewhere on that dotted line, the two lines are going to cross each other. At this point, I don't know where, but I do know that somewhere on that line is a solution. So I can find out by taking my x equals negative 1 and plugging it into one of the equations. It does not matter which one, but I might as well plug into the one that I've already saw for y. So I plug it in, and I get negative 2 times negative 1 is a positive 2. Positive 2 minus 4 is negative 2. So my solution, it's the set of the ordered pairs negative 1 comma negative 2. And then you can verify this graphically. So there's my blue line and my red line, and they do cross right there at negative 1, negative 2. All right, for this last example for solving systems by substitution, I'm going to show you, I'm going to spoil it a little bit, but I'm going to show you what happens when it kind of seems like it falls apart, when we don't end up with an x comma a y. So it's one of those other two. We'll get like a true or a false statement. So I have these two equations, so we need to solve them for y or x, so we need to solve them for one of the variables. And I noticed that that singular y just is screaming at me. That one's the easiest to solve for, so let's do that. So I'm going to take my blue equation, subtract 4x from both sides. So I have y equals negative 4x plus 11. Take that, I plug it into the other equation. It has to be the other equation, that's why, again, the color coding. So I put into the other equation, and I distribute the 3 into the negative 4x plus 11. And when I do, I distribute that, and I get 12x minus 12x plus 33 equals 33. Notice what happens with the 12x's. 12x minus 12x, they cancel to 0. And I'm left with just 33 equals 33. Does 33 equal 33? Yes, always and forever. This is a true statement. Now, this kind of true statement would occur always, even back on this other equation. If I would have taken this, if I would have accidentally taken this right here, this y equals negative 2x minus 4, and plug it back into itself, I would get a true statement because they're the same line, right? But here, I'm getting a true statement, but I plugged it into the other equation. That tells me these two things are actually the same line. This is true always and forever. I don't care what x you pick, the resulting y is always going to give me is always going to equal each other. I don't care what y you pick, the resulting x's are always going to equal each other. It doesn't matter what you pick, it's going to equal each other. So if I was to graph them, you see that they are literally the same line. They're on top of each other. I graphed the blue as a dotted line, and then the red as just a solid line, and you see that they are on top of each other. So how do we write our solution? Because it's not all ordered pairs. There are an infinite number of solutions, but it is not all ordered pairs. All right. The reason why it's infinite is because it's all the dots you see here in this segment from negative 10 to 10, but then all those that go up to infinity and all those that go down to infinity in that direction. So there's a lot. So how we write our solutions is a little bit specific. So this is a little math notation, set builder notation is what we call it. So let me read this for you. So this is read as, I'm opening, this is the set bracket. So it's the solution is the set, this is a set of all ordered pairs x and y, such that, this vertical line is such that y equals negative 4x plus 11. All right, so this is defining the relationship between x and y. Now we can put any equation here, but I like to put the one where you've simplified. You've already have a y by itself or an x by itself. So I'm saying that it's all x's and y's as long as it meets this requirement. So let's look over here graphically. like I said, it's all the points on this line, right? And that's what I'm saying, right? If I was to graph this line at 11, slope of -4, that's this line. I'm saying it's every ordered pair on this line. So it's every ordered pair on that line. Fancy math talk. It's the set of x's and y's, the set of ordered pairs x and y's, such that, fancy talk for just when this happens, that relationship is true. So it's saying all ordered pairs on this line. All right? So that's how we write that's how we write our answer when it's an infinite solution. In the next video, we'll be talking about instead of substitution, we'll be talking about the elimination addition method. We'll also see a time when we end up with a false statement, and then we'll do a little bit of practice where you get to pick whether you want to do substitution or elimination, and maybe how you might determine which one is easier. So I'll see you in the next video.